Okay, but now let me introduce our today's speaker, Professor Richard Gill. I will give a very short introduction. Gill is professor at Leiden University. He is a world well-known statistician, a member of the Royal Netherlands Academy of Arts and Science. In statistics, he is most well known for his research on counting process and survival analysis, some of which has appeared in a widely used textbook, statistical models based on counting process. This book, which is often referred to as ABGK, short for the authors. Besides the work in statistics, Gill is also well known for his voluntary consulting and advocacy on behalf of victims of incompetent statistical testimony, including a Dutch nurse who was given a life sentence for serial murder, and her conviction was overturned. Gill is also a pioneer in quantum probability and statistics. That's why we invite Gill to give this talk today. One of his contributions is the development of the statistical methods used to analyze the entanglement experiment in Delft, which is a very important experiment that earns the laureates this year's Nobel Prize in Physics. Gill has given a short course on quantum statistics and probability in October 2019. Today we again welcome Gill to give this talk about this year's Nobel Prize in Physics and the relationship to statistics and code inference. Okay, let's welcome Professor Richard Gill to give this talk.
Thank you very much indeed. It's wonderful to be kind of back in China again, because I had a really fantastic 3 weeks when I was there 3 years ago, I think. So I hope you can see my slides now. Yes. And you can probably see me double the second piece of the time, because this was in '64, and there were young people who were rebelling against the establishment. Let me say, the establishment in physics at that time was quantum physics. Quantum mechanics is great. It works. We use it. We do fantastic things with it. Actually, we don't really understand it. We don't even say that we don't understand it. It's forbidden to talk about what it means. There's a famous dictum of the famous Feynman who said, and it's shut up and calculate. So the philosophy at the time was, we have got this fantastic mathematical structure which describes reality incredibly well, and we're using it to discover new and fantastic things all the time, and we're doing great experiments, and technology is coming out of it, like, you know, semi-conductors, atom bombs, you name it, everything was coming out of quantum mechanics. Earlier in the history of quantum mechanics, there had been debates and fights about what it actually meant, because you have this weird mathematical structure with Hilbert spaces. And the Hilbert spaces were not, I mean, they were not the real space out there, but they were much higher dimensional, and they.
Sorry, Richard.
Yes.
Are you moving the slides? But we are keeping seeing the first page of the slide.
Yes, but I will be.
You're talking about the first page. Okay.
Yes, I'm giving you a little bit of historical background.
Sure.
Philosophical background.
Yes, go ahead.
Okay, so
sorry about.
Yeah. Please say things like that from time to time, because I have a tendency to start telling big stories when I see one of my favorite pictures in front of me. Well, I was telling you that, let's say the story started with John Bell with a paper in 1964, which had no impact at all at the time. It took a long time before people started to notice it. And to begin with, people thought this is rubbish on the whole. And people said, a couple of people started getting interested in doing an experiment outlined by Bell. And one of the first ones was John Clauser. And his supervisor said, don't do this experiment. John Clauser visited Bell, and Bell asked John Clauser, have you got tenure? And Clauser said, well, yes, yeah, I've got tenure. And Bell said, okay, well, then you can do the experiment. But if you haven't got tenure, don't do it, because it will ruin your career. So that's how it was in those days. Anyway, Clauser is here, John F. Clauser, for many reasons, because his name will come back a number of times, but he also did the very, very first experiment together with a student, and that was in 1972. And the experiment confirmed what Bell had thought, which was that in quantum mechanics, things are predicted which look as if they are non-local. They look as if there is influence from far away, instantaneous where you are. And this was and is, well, certainly was deeply unsettling to, but really all physicists. Well, Aspect was one of several other people did experiments. There was also an experiment which did not confirm Bell's work. There were a couple of more experiments which did. In 1980 or 82, yeah, published in 82, Alain Aspect in France did an even better experiment than Clauser's, and it again confirmed Bell. And this time, or by now, everybody started to notice. Okay, what I wanted to mention is that the names you see here are basically the survivors, because there were plenty of other people who did incredibly important things. And yeah, life being what it is, and humans being mortal, many of the big names of the early times are now passed away. So we'll see some of those names also. Right. I don't know if I'll tell you more about the little cartoon here, but it's a drawing by John Bell in one of his best papers. And I'll certainly be talking about that paper. Now I see if I go to the next slide. Yes. Okay. So there you see Aspect, Clauser, and Zeilinger in alphabetical order, as they are today, more or less. And actually, Clauser, if we would put them in order of their most important works for which they got the Nobel Prize, then we should have Clauser first to the earliest experiment, Aspect with a mid-period experiment, and Zeilinger with the latest experiments, but also Clauser and Zeilinger and also Aspect having really important theoretical contributions, which I will tell you about. Here's a picture of John Bell, and he's looking at a Christmas present he just got from his friend. He was essentially a theoretical physicist, a particle physicist, high energy particle physicist, and he spent most of his life, his academic life, working at CERN, at the big accelerator in Switzerland, in Geneva, I think. Like during the daytime, he did very important work on particle physics for the CERN experiments, but in the evenings and in the weekends, he worried about the foundations of quantum physics. And he kind of kept those two lives apart. And like his colleagues at CERN didn't even know that he was writing these weird papers about the meaning of quantum mechanics, which, as I mentioned, was a kind of taboo subject for sort of serious working physicists who wanted to publish papers and do, you know, get Nobel Prizes and so on. They did not work on the foundations of quantum mechanics.
Yeah,
okay. Yes.
And Richard, yeah, hi. Thank you so much. That's a kind interaction on the history of the quantum foundation work. And that's as mentioned, in 1976, Krauss bit to John Bell. That's the John Bell. That's the very interesting story about that. You get to the tenure or not? Such kind of question, interesting question. It's on that hand, in that as you said, is that other many groups in that did the experiment on that not succeeded on the violation of the Bell inequality. There's how many groups in the world in that 1976 in that's interesting in that the experimental demonstration of such kind of experimental demonstration work.
Sorry, you're asking how many books there were?
Yeah, how many groups?
Groups, how many groups?
Yeah.
How many groups? I think essentially 2. And I put on this slide the cover of a book, which is really, really worth reading. It's really nicely written by a very good physicist. His name is Adam Becker. And the book is called What is Real? And he tells the story of who did what, when, and who had contact with whom, and how the people met. And you get a glimpse of a network of different groups of people in different places who were all moving into the future. And it's fascinating to read. There's an enormous amount of coincidence and chance in there. All right, people happen to go to some place, happen to hear some talk, go back, get excited, talk to some more people, and things happen. And you see that the connections are, which actually drive that science, innovative science, they're coincidental, they're kind of random, and they're personal. There's personal connections every time, which is a story you could tell about other fields of science as well. Okay, so I wrote some on this slide some sort of keywords and phrases, and I put the names of the persons on the bottom of the slide so you can maybe start to notice them. EPR, we will be talking about EPR, and that stands for Einstein, Podolsky, and Rosen. And that's a paper in 1935, which is one of the most cited papers in the history of science, probably. And it was a part of a discussion, a debate between Einstein and Bohr. So Einstein founded relativity, Bohr founded quantum mechanics, you could say. At least they were major leaders. And that Einstein Podolsky Rosen was an example. Well, okay, I'll tell you more about it in just a moment. But that paper is the other place you could put the start of everything in 1935. Well, I've shown you a picture of John Bell and told you about his work. Aspect did a really breakthrough experiment in 1980 or so, but his experiment did not test Bell's inequality from 1964, but a slightly more sophisticated inequality, which Bell could easily have thought of, and Bell immediately adopted it himself, and it's called the CHSH inequality. And that will come back in this talk all the time. And CHSH, they are Clauser, Mr. Clauser again, and Horn, and Shimoni, and Holt. And I suspect that Horn, Shimoni, and Holt have all passed away by now. But Shimoni, you'll see the letter S in a later acronym. Shimoni is also one of the key persons who could have got a Nobel Prize. And he is an interesting person because he actually came from philosophy and moved into physics, or the other way around. I forget. No, he started in philosophy and moved into physics. And his name keeps cropping up because he invented fantastic theory, as well as worrying about the foundations. CHSH, inequality. Well, later we'll get to GHZ and GHSZ, and the H is of Horn, who is also in CHSH, one of those. H's, right? So like Horn and Shimoni are people who also could easily deserve a Nobel Prize, and if they had been alive today, which they could have been, then they might have been on that list of 3 instead of, or together with. Right, and at the end of the talk, or towards the end, no, I'm going to start in the beginning, also talking about it. I'm going to talk about what is going on right now. And one of the things which is going on right now is called device-independent quantum key distribution, which is about a technological application of this whole stuff for technology, which is being designed and tested and engineered and maybe even sold already to companies. And possibly it doesn't work quite as well as it's claimed to work yet, and maybe it never will. But that's one of the applications of this whole business. And I will come back to that a few times. Right. Now, okay, so in fact, I'm going to start. Right, now this is where we start with a little bit of fun. I'm going to explain to you how to do quantum key distribution yourself at home, preferably with a friend. I mean, like with 2 people in 2 different places can do this. That's how they should do it. And they should be well separated, and but they should have a phone line between them so they can talk to each other. And the phone line may be being intercepted by enemies. So they have to be careful what they say over the phone. Their task is a very simple task, and it's a task which you could imagine is impossible. Their task is to create shared randomness which nobody else in the world can know. They want to generate a random key for future cryptography, for sending encrypted messages, again over the phone lines, but encrypted. But they want to create a key for the encryption, and they should both possess the same key, and it should be secret. But they're far apart. So how the hell are they going to make a key together, sitting in their 2 offices, like one in Beijing and one in Shanghai, or Barcelona and Beijing for that matter? They're sitting there far apart. But of course, they've had communications in the past, and they set things up in the past to arrange how they can do it now. And this is how they could do it, and how you can do it with your friends. It won't be as secure as the quantum version, but you'll see the idea. So to start with, we need 2 apples and 2 oranges. Okay, there's a picture of them. They're just 2 apples and 2 oranges. And we need 2 bedside tables. And I went to the website of IKEA, I think, and I found this one, which was a rather nice picture because it has got the 2 chests of drawers, right? I don't know how well people's English are, but this is a chest of drawers. These are 2 chests of drawers. And there's also a clock on top, which is important because there's going to be timing involved in this. And Alice and Bob, they are always, oh, it doesn't say that yet. The 2 people in the 2 rooms are going to be called Alice and Bob, as they always are in cryptography stories. And Alice and Bob also have clocks, and so they're able to coordinate when they do things very carefully. Okay, so what they do in advance is they, like go down to IKEA and get these chests of drawers, and they go to the market and get 2 apples and 2 oranges, and they arrange, they fill the drawers, 4 drawers, each with 1 fruit, in a completely randomly chosen, but out of 2 possible configurations. So either Alice puts her apple in the top drawer and the orange in the bottom, and Bob puts his orange in the top drawer and his apple in the bottom, or they do it the other way around. Okay, is this clear? We've got 2 chests of drawers. There are 4 drawers. There are 4 fruits, and they're either arranged in configuration 1 or in configuration 2. And those that choice of which configuration is done by tossing a fair coin. And everything is secret. No questions? No questions in the chat. Okay, so that's they are connected by a public phone line. They're sitting in their rooms, each with one of those chests of drawers, and they don't know and they don't need to know, and it should be a total secret. It's an absolute secret whether they are in configuration 1 or in configuration 2. Now, this chest of drawers has got another feature, which is that when you open one of the chests, when you pull out one of the drawers and look what's in there, well, basically the whole thing explodes. Doesn't kill anybody, but it all goes away. So what happens is you get to see what is in one drawer, and the other drawer is locked or whatever, and that's it. So you can only open one drawer, and you can look in one of the drawers and see what's there. So Alice and Bob each toss a fair coin, and they keep secret what the outcome was, heads or tails, and they open a drawer. They each open one drawer according to the outcome of their fair coin toss, the secret fair coin toss. But then they do get on the phone to each other, and they tell one another whether they opened their top or their bottom drawers. Right, so it could be that they both opened the top drawer, or they both opened the bottom drawer, or Alice did the top and Bob did the bottom, or vice versa. But whatever way, they now know that they either both saw the same fruit, or they both saw a different fruit. They both know this, and whether they both saw the same fruit or both saw the different fruit is it's known to both of them, and it cannot be known to anybody else because everything was secret so far. So what they have actually used altogether is like 3 fair coin tosses to set up the whole business. One at the start, choosing configuration 1 or 2, and then each a fair coin toss to choose which drawer to open. And what they have managed to engineer out of those 3 fair coin tosses is 1 fair coin toss, which only they can know the outcome of. Is that clear? It doesn't matter if it's not clear, but you may want to think about it some more. My slides are on the internet. Okay, so that simple idea is actually the easy part of something which is called quantum key distribution, which was pioneered by a number of people. And what I'm telling you about is part of the BB84 protocol, as it's called. So the idea has been around for a long time. And quantum key distribution is a big field, which is big and getting bigger all the time. Okay, but there was nothing quantum here, right? This was absolutely classical. I mean, these were just chests of drawers from IKEA and apples and oranges from the market. Now, there is an important connection with this story and with what EPR did, Einstein Podolsky Rosen, in 1935, because they discussed a situation in quantum mechanics in which Alice and Bob were in 2 different locations, and they could each either measure the position or the momentum of a particle. There are 2 particles which have gone from a central location to Alice and Bob. They can each look at their particle. They can measure its position or they can measure its momentum, but they can't do both. Quantum mechanics even says you can't, and physicists will agree that it's not possible. They can measure either the position or the momentum. That's opening the top drawer or the bottom drawer. And when they've done it, they will know what the other person would have done if they had done the same measurement. So if they would both measure position, they would get positions which are, sort of equal and opposite. If they both measured momenta, they would get momentums which were equal and opposite, right? So they each know that if they had done either of their possible measurements, they would know what the other one would have got if they had done either of their two possible measurements. And Einstein, Podolsky, and Rosen said, well, this shows that the dogma of quantum physics, which is that the position and the momentum don't exist until they're measured, and it makes no they kind of come out of the act of measurement. This dogma is wrong, because clearly the position and momentum must already be sitting there in both of those particles, because Alice, by doing some measurement on her particle, can find out what Bob's momentum is, and if she did a different measurement, as a counterfactuals here, there are two experiments which Alice could do, and each of them would determine what Bob would determine the position and momentum of Bob's particle for Alice. Clearly, there is no action at a distance. Alice's measurement doesn't change Bob's particle. Therefore, said Einstein, Podolsky, and Rosen, they said, therefore, either quantum mechanics is wrong or it's incomplete. It only describes some surface aspects of reality, but it doesn't talk about things which are real. That was the point of Einstein, Podolsky, and Rosen. Now, Bell's contribution to this was that he, in some sense, slightly, he modified the Einstein, Podolsky, Rosen example. He started talking about spin of a spin half particle instead of position and momentum of a particle in motion, which makes the story simpler because it's binary properties. But he allowed Alice and Bob to do different measurements to one another. Alice could measure one of two things, and Bob could measure one of two things, and those things were different. Like 4 different things were being measured, certainly by the time we get to CHSH. So Bell took the EPR example, made it slightly richer, and came to the conclusion either quantum mechanics is wrong or it's not local. So he had a very dramatic pair of choices, both of which would be great shocks to the physics establishment. Either quantum mechanics is wrong or it is not local. There is some sort of action at a distance. Okay, this is one of the reasons why Bell's work was ignored for a long time, because nobody was willing to even think of either of those possibilities. It was just, I mean, it was clearly wrong. Clauser wrote, he saw Bell's paper, he read it, and he sort of knew it must be wrong. He spent days and days looking for the mistake in the maths, which is very simple maths, as you will see. And he couldn't find it. And he believed in locality and in realism, and he didn't believe that Bell was right, but he couldn't find the mistake. And this drove him to want to do his experiment. And the same mentality is what drove Aspect also. Okay, now, so now I'm moving into quantum mechanics. And there are really there are a number of issues with the apples and oranges story. I mean, it's not very practical, right? And especially not if you want to make 1,000 random bits in order to do some serious cryptography, right? You have to go get 1,000 pairs of these mysterious bedside tables from IKEA and do a lot of heavy-duty lifting to set everything up. And okay, and suppose at some time this is kind of become mainstream, and you can go to an electronics store and buy some apparatus for doing it. which is the situation now, in fact, can you trust the manufacturer? They sell you something, and on the package it says guaranteed, secret, blah, 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 quantum, blah, 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 blah. Can you trust them? You get 2 boxes, you take them to 2 different places, you do it. Can you really trust them? Maybe they're lying, maybe they're fooling you. Okay, so there are 2 important things here. One is the practicality, and the other is the trust issue. And now the trust issue, that's what the device independent quantum key distribution means, because it means you get 2 devices, you can test them, but you can't take them apart. You are just able to use them. Can you use them, and by using them collect data which will prove to you that they are doing what they're supposed to do, right? I mean, of course, when you use them, you don't know that people are not listening in, or that you're not being fooled and so on. So you only can look at the actual output of the boxes. You're not allowed to look into the boxes, and you're not allowed to make any other assumptions. You can't allow that you're in a, I mean, you want to use these out in the real world, and for running your spying network or doing your internet banking or whatever. So testing them in a laboratory is not good enough. Testing them in a top secret laboratory is not good enough. You need to test them in the field. Can you do that? Now, that's what can be done according to quantum mechanics, as we will see. No, well, as I will suggest, I guess. Okay, we also have to get the practical business of doing it. Okay, there's a tiny little bit of quantum mechanics formula there. 1 over the square root of 2 apple orange plus orange apple, and I'm going to explain what this means. The orange and the apple here are just labels. I mean, they are just pictures, right? Later, we will do things like writing 0s and 1s there, and they're just labels. They're just names. And Alice will have a label on her part of a quantum state, and Bob will have a label on his part of the quantum state, and Alice's labels will be 0 and 1. Bob's labels will be 0 and 1, but Bob's labels don't mean the same thing as Alice's labels. They are just labels, right? And there is just a binary choice, and Bob could rename his 0 and 1 as 1 and 0. That's allowed. And so, okay, things to notice. Okay, so here there's a little bit about the weirdness of quantum mechanics. You start off with a quantum state of 2 particles, 1 over the square root of 2. That's a normalization factor, because actually these 2 things inside the round brackets are 2 vectors of unit length in a Hilbert space. They're orthogonal to one another, and they're both of length 1. So the 1 over square root of 2 makes this combination of the 2 into another unit vector, unit length vector. It's a complex Hilbert space. I mean, I could have put in some complex numbers in here as well, but I don't need them at the moment. But it's a complex Hilbert space. And actually, the Hilbert space where this big formula lies is just C4, a vector of 4 complex numbers, right? Well, right, that's, yeah. Okay, now here is a little, okay, this is just telling you how DIQKD, device independent quantum key distribution, works in practice. Alice and Bob should somehow create this quantum state. Don't worry about it. It's a weird thing. It's a wave. It's all over the place. It's nowhere. It's everywhere. That's what people argue about if they're philosophically minded. It's a mathematical object. It is very useful for doing calculations, and the calculations describe perfectly what we see in the laboratory. So it's good for something. Okay, Alice and Bob should create 2 spin-half particles in this state many times anew. And each time they should measure their own particle in several different ways. They will communicate using public classical means about some of their results, and they'll keep other of the results secret. They will either determine that they really did have two quantum particles again and again in that special state. And therefore, and in that case, if that was the case, it means, according to quantum mechanics, that nobody in the universe can know anything else about what their measurement results were. Nobody else has any access to that state. It's in those two particles only. Quantum mechanics promises this, and we believe in quantum mechanics. That either they will find that they indeed had succeeded many times in creating their two chests of drawers, or they will discover that somebody's been listening in, or there's been some mechanical leak or failure of the apparatus, and they will know that they'd better abort and check their security and start again. So with high probability, and there is probability in this, with very high probability, if they do it enough times, they will either end up with very many shared secret bits, or they will abort their mission. That's what happens. That's the roughly device-independent quantum key distribution. Okay, and it's being sold to banks and spying agencies already. So so those are the two questions: how to create that state, and how to be sure that you have got something in that state. Two questions. And here's the short history. And I have actually said everything there already. And I put the dates there. 35, Einstein, Podolsky, and Rosen. Assuming locality and realism, QM, quantum mechanics is either wrong or incomplete. Bell 64, assuming the same things, locality and realism, QM must be wrong. Right, that was a shock. And it was so shocking that nobody took any notice. And anyway, he couldn't get it published in a regular journal. It was in an obscure journal, which nobody noticed. Okay, I've explained the EPR scenario and what Bell did. And I've pointed out that according to quantum mechanics, certain sets of correlations between different things, between the measurement outcomes of different measurements, which two persons can do, certain sets of correlations can only be achieved with certain states and certain measurements. And anybody else who's looking in would destroy it. So if they get to see those correlations, then they know that nobody else knows what they have seen. Nobody else can have seen what they did see. So they know they've got, and they know it's completely random what they saw. Absolutely, completely, utterly random. Okay, so now here's a little bit of math. Any questions? So I'm hoping everybody knows a little bit about complex numbers, but not hardly anything, and knows about a vector space, really. That's all you need to know. And we are tensor products or outer products of two vector spaces, which is just C2 tensor C2. You take a complex 2 vector and another complex 2 vector, and you write down all the 4 products, and you get a complex 4 vector. So that's what we're doing here. And we start off with, well, this is just notation. Let 0 and 1 with these funny brackets, which are called kets, but it's just to let you know, like a picture, that these are 2 column vectors. You can think of these as 2 column vectors, and let them be an orthonormal basis of C2. Okay, there are lots of different orthonormal bases of C2, obviously, but it's just any orthonormal basis of C2. Now, actually, we're going to have 2 copies of C2, and we're going to have 2 orthonormal bases of C2, and they don't have to be the same orthonormal basis. They're just any 2 orthonormal bases of C2. And starting with that, we can form an orthonormal basis of C2 tensor product C2, which is just C4. And here's the pretty notation for that in the middle of the slide. Yes, and can you see my pointer? Can you see my pointer? Yes, okay, it works a bit slowly. So these are important. This is very important notation. I made my pointer as big as possible. 0, 0, 0, 1, 1, 0, 1, 1. They are on an orthonormal basis of C2 cross C2. And they are like the apples and orange basis. 0, 0 corresponds to a situation where if Alice looks at her qubit, whatever it is, it's a physical system having a property which can be modeled in this way. If Alice would look at her qubit, when the two qubits together are in this state, she would certainly see a 0. I mean, she would get to see in the real world a 0, or I mean, the label 0. She would know if Alice and Bob know that they have one of these 4, and they each separately look at their qubit, they will find 0, 0, or 0, 1, or 1, 0, or 1, 1. They will know which one they have. If Alice measures hers, she will get to see, and it's 0, 0, or 0, 1, she will get to see a 0. She won't know what Bob has. He might have the 0, or he might have the 1. Okay, so here's an orthonormal basis of C2 tensor C2. And here's another one, 4 vectors. Each of these 4 are unit length. They're all 4 orthogonal to one another. Here is a combination of 2 of them, and here's a combination of the other 2. And you can just do the math. I mean, it's a back of an envelope, small envelope. You just need a small envelope, or you see it immediately. These 4 vectors, which I've written here, right, with a plus or a minus and a plus or a minus, that's 4 new vectors. They are also unit length and orthogonal to one another. Now, they are called, this set of 4 is called a Bell basis. It's an orthonormal basis of H cross K in my notation. And the 4 vectors are also called Bell states. They are possible states of 2 qubits, but they are entangled states, so-called quantum entangled states. They together, they embody properties of the pair of particles which cannot be, can't be described by thinking of those 2 particles separately. Cannot be described by thinking of those 2 particles as being completely separate physical things. You can only get this state by preparing them in some way together. You have to make them that way, and that will involve communication in the past between Alice and Bob in order to create any of these states, or other things in the past, in the joint past. Okay, I'm going to focus on this particular one of them. It's just one of the 4. In fact, you can change any one of the 4 into any other of the 4 by flipping labels and by flipping signs, which doesn't make any difference either. I mean, doesn't make any difference to the physical predictions. So they are
what's the meaning of ONB? What's the meaning of
ONB? Yes, I said that many times. Orthonormal basis.
Thank you.
Okay, orthonormal basis. Ortho means orthogonal, normal means normalized, basis is basis, right? A basis of 4 unit vectors. I should say unit length vectors. Yeah. Okay, now here's some more of this tricky stuff. So now so here's a little sort of, I mean, this is the math bit, which nobody understands. I mean, you can understand the math, but what is actually really going on is sort of the question, and nobody knows really, and maybe nobody can know. Maybe it's beyond human comprehension. But anyway, we've got the math, and we can build the machines, and it works. So this is about measurement of quantum states. So you think of H and K as being the Hilbert spaces describing a property of something which Alice has and something which Bob has. And they can each do all kinds of things with it. They can measure it, and they will get classical information out of it. They will see something. In particular, this is not the only things they can do, but the most standard things they can do will have a binary outcome. They can look at their particle, and they can look at their particle, or whatever it is. It may be a device, even. It can be a piece of a semi-conductor. They can look at it in many different ways. When they look at it, they get to see, it's like asking it a question. Are you spin up or are you spin down? Okay, and the particle will say, yeah, I'm down. You could also ask, are you spin to the left or are you spin to the right? And the particle will say, okay, yes, I'm spin to the left. But you can only ask one of those questions. You can only ask one question once. Once you've asked it, it's gone. That's quantum mechanics. The mathematical formalism says that is how the world is. And nobody understands it, you could say. Feynman said, anybody who thinks they understand it doesn't. So the first test of when you hear somebody trying to explain quantum mechanics to you, if they claim that they understand it and that they can make you understand it, then they don't. Then you know you shouldn't be listening to them. Okay, so I don't understand it, so you can listen to me. Right. So they can each choose a basis, an orthonormal basis of their own part of the Hilbert space, H and K, C2 and C2, and they will get to see, it's asking their particle a question which has a yes-no answer, and they'll get a yes or a no answer. The yes and the no answers each correspond to one of the two elements of the basis they used. And here, this ket with the letter A written in it is just, yeah, it's just the name of the orthonormal, of the element of the basis of C2, which gave the answer which Alice got. Right, so you could say, let's call them A and A prime. And the particle said, A. Alice asks, are you in A or in A prime? Those are just two orthonormal vectors of C2. And the particle will say, I was in A. And Bob can ask a similar question to his particle. And the particle says, I was in B. Both particles are now gone. And here's the formula for the probability of their answer. And the only thing you don't know here, but I told you already what psi was. That was the previous slide. Okay, but doesn't want to go there now. Or this way. No, okay. Oh yeah. No, sorry. Oh my God, I'm losing control of my, I want to go back. Yes, okay, here. This was psi, so vector in C4 of length 1. Psi dagger means the transpose and complex conjugate of that vector of 4 complex numbers. So this is a row vector of 4 complex numbers, and this is a column vector of 4 complex numbers. And we dive bomb the horizontal one into the vertical one, and sum the products and take the absolute value, because it may be a complex number, and we square it. And according to the maths, I mean, you can sit down and do some homework later if you want to get into this, and you can find out that if I have here A or A prime and B or B prime, two pairs of orthonormal bases, then I get in this way 4 probabilities which add up to 1. I mean, 4 non-negative numbers which add up to 1. So this determines probability distribution, the joint probability distribution of Alice and Bob's measurement outcomes when they each do things to their particle, if it is in that state. And so what if they could make that state many, many times, exactly the same way, and do those measurements many, many times, they would get to see the whole probability distribution in limit of large numbers. They would learn those 4 probabilities. And there's something called quantum tomography, which says that if they do enough different measurements, so not always the same ones, but Alice does lots of measurements, Bob does lots of measurements, they collect all the statistics of all those measurements, every time making this state psi again, they will learn enough to determine the state to as much accuracy as they like. So this state is some psi is sort of real because you can find out what it is, but you can only find out by doing many, many measurements on identical copies. So you have to know that you have got many identical copies, and you sort of should know what you're doing. Okay, now I'm going to maybe go over the next slide very fast. But let me just mention that to every orthonormal basis, there corresponds a so-called Pauli spin matrix. Like, so 0, 0. So this is like eigenvalue plus 1 times this, a column vector times a row vector, which is actually a matrix. And this is the eigenvector decomposition of a 4x4 matrix, sorry, of a 2x2 matrix. These are 2 vectors. So this thing here is a 2x2 matrix. So this whole thing is a 2x2 matrix, and it's it has eigenvalues +1 and -1, and it has eigenvectors 0 and 1. Of course, the eigenvectors are only determined up to normalized eigenvectors even are only determined up to a complex so-called phase, namely a complex number of absolute value 1. So I'd say these are the eigenvectors, but actually you could put any complex number here and here of absolute value 1, and they would also be eigenvectors. So we should really talk about eigenspaces. Okay, now here's some formulas which I don't think I'm going to use at all, actually, if I remember correctly. But there's something here called a density matrix. There's some formalism here. Well, there is some formalism here which is very useful for doing the calculations to get the answers which I'm now going to show you. So I'm not going to spend more time on these right now, because I look at my clock. Oh my God, sorry. Okay, time goes fast. So let's move on. What did I want to say at the bottom? Okay, right. So here's a description at the bottom of this slide of 2 different measurements which Alice could do. She could measure the spin of her particle in the X direction, or she could measure it in the Z direction. Bob could either measure this or this. You can do some math, some sort of geometry, and some isomorphism between unitary matrices in unitary 2x2 matrices and real 3x3 or orthogonal rotations. I mean, there's some beautiful math and geometry here, connecting complex things in C2 with real things in R3. No time for it now. These 2 possible measurements of Alice is she could either measure her, of Bob, sorry, he can either measure his particle in this direction, and he will get it's pointing this way or it's pointing that way. Or he could measure it in this direction, and the answer will either be it's pointing this way or it's pointing that way. And we can just sit down and do the calculations and find the probabilities of, we can find 4 sets of 4 probabilities for the 4 combinations of what Alice could do and what Bob can do. And here are the results. Well, first of all, Alice and Bob only get to observe +1s and -1s. You can do the calculations, which I haven't shown you the formulas for. Well, I mean, they have been there, but you didn't absorb them. They are simple calculations, a little bit of matrix algebra, 2x2 matrices, 4x4 matrices. You can do it all on a few backs of envelopes or beer mats. You will find out, according to the rules of quantum mechanics, the expected values of those +-1 outcomes are all 0. And therefore, the only interesting thing, well, the most interesting thing are the correlations. And the physicists say correlation, but they just mean the mean value of the product, which is, of course, the same if you're talking about random variables, which take the values +or -1 and whose mean value is 0. The expectation, the variances are 1, the expectations are 0, so the correlations are also the expectation of the product. Okay, and the expectations of the product are 1/√2 with a plus sign in 3 cases and -1/√2 in the 4th case. And this is the stunning fact which John Clauser couldn't believe when he first did it, the calculations, tried to do the calculations. And why is it stunning? That's what we will see next. Anyway, but just to recall, to summarize, there are this is an experiment with 4 sub-experiments corresponding to 2 choices for Alice and 2 choices for Bob. They're experimental choices, they're settings which Alice and Bob can choose. There are like 4 sub-experiments, and we get 4 correlations. We predict 4 correlations. 3 of them are +1/√2, and 1 of them is -1/√2. So the sum of 3 minus the 4th is 2√2. Right, now you will, many of you will be very happy that we're going to forget quantum mechanics now, and we're going to look at this experiment from a classical point of view. We're going to ask ourselves, could classical physics, does it allow these experimental results? And we can take any physical theory we like, but it must be prior to quantum mechanics. Okay, and then, okay, so don't talk to physicists. They will say, well, we know quantum physics is true, so we have no use for this. Okay, they're right. But okay, on the other hand, they're trying to make money and get research grants doing DQ, device-independent quantum key distribution. And it has led to this. Sorry, I mean, this has led to that. Could there be a classical physical explanation of these correlations? Now, first of all, I want to show you what the big thing about Aspect's experiment was relative to Clauser's experiment. So it's like 15 years went by before they could get so far. Aspect arranged that the 2 qubits are far apart. Well, I mean, they were like 10 meters apart. But okay, that's a macroscopic distance. They were 10 meters apart. And at 10 meters apart, well, in fact, what was happening in Aspect, there were 2 photons speeding away from some source where something had been excited by a laser, and 2 photons shot out like this and reached opposite ends of his lab in Paris, or near Paris, at Orsay. And at those 2 places, the 2 photons were each measured. Their polarizations were measured. and their polarizations were measured in directions which were chosen while the photons were flying through the air. And the photons which arrived were measured by photodetectors so fast that Alice's photodetector could not possibly know how Bob's photon was being measured. The distance between the two ends of the laboratory were so large that the signal from traveling from one side to the other at the speed of light takes longer than the time interval, well, there's a little spelling mistake there, than the time interval between the choosing the setting and getting the outcome on both sides. Okay, that's what Aspect did for the first time. And Bell, he discussed this with Bell in advance. Bell checked that he'd already got, I think he did not have, he did not yet have tenure. So, and all his colleagues thought he was crazy to do it, but he did it anyway. Okay, now he's got the Nobel Prize, so, and he deserves it. Right. Okay, now this is a diagram from, I think, Bertlmann's, Bell's absolutely most brilliant paper. And the paper was published in 1981 in some obscure French, in a sort of in a kind of private journal. They were like papers which were circulated among the few crazy people who were interested in this. And this one came out in 1981, and it was based on a lecture Bell gave in Paris, I think, to French philosophers of science. And he explains in that paper very carefully how you should do a decisive experiment. And this is the diagram he gives. And the thing is that the experiment should somehow be device independent. You do not make a physical model of what is going on inside that big long box. That big long box is just part of the two laboratories of Alice and Bob, and everything in between, and the cables which are connected them, because there are photons going through glass fiber cables, and the photodetectors. Everything in the big white box, in the middle is a black box. And all we do is observe the correlations between what comes out. The important thing is that Alice and Bob at the two ends get to choose what to put in, and they can choose different things to put in. They can choose a setting. There's a device there. They can turn a knob and it points at a dial, like on a machine with a dial which you can set. They can set it. Alice can set hers. Bob can set his. Right, that's A and B. Somebody in the middle is perhaps responsible for setting things up so that things happen in the middle, that particles are going to arrive there. Okay, and it may or may not succeed. So the guy in the middle, who's often called Carol, sometimes Charlie, he presses a button which excites a crystal by a laser, and then some physics happens. So he presses a go button, and it may or may not succeed. It might not succeed every time. Doesn't matter. He gets to see yes or no. It works. But Alice and Bob don't necessarily know whether Carol got the yes or no outcome. They just do their measurement anyway. They just do it anyway. Later, Alice, Bob, and Charlie get together and they correlate their results. And there's very precise timing information so that they can say, well, like this was here was a trial where Charlie pressed go and got yes. Alice pressed this button and got -1 or +1. Bob pressed this button and got -1 or +1. And okay, I'm going to model Alice and Bob's choices as coin tosses. I imagine them each sitting, tossing a coin, lots and lots and lots of times, possibly millions of times, because Charlie might be pressing the go button millions of times, but maybe almost never getting a yes answer. And that's how it actually goes in the lab, as I will probably mention. Okay, right. So finally, we're going to look at the data which the experiment gives us in those situations when the go resulted in yes. And so for those situations, we just have Alice's input, Bob's input, Alice's observed output, Bob's observed output, and I'm going to model them as 4 binary random variables. And here you will be pleased at last to see a classical physical model, and it's a causal model. It's a model from the present day theory of causality. There is some, and this is a model for one run. Sorry, I will call it one trial. This is going to be repeated many times. Maybe millions of times. And I'm interested in the situations only when there is where Charlie got a yes answer, and I've left Charlie out of the picture, so I'm conditioning on the yes answer for Charlie's go. Alice and Bob are tossing coins to choose settings, and the coin outcomes are A and B. And I let them be 1 and 2. Okay, heads or tails I could also write H and T here. 1 and 2 is more convenient. As you can see from this causal model, I'm allowing A and B to be dependent of one another. So I'm allowing that Alice and Bob in advance choose settings which they're going to use together in some dependent way, any way they like. So A and B may be dependent, but as you see, I put it sort of out to one side, and according to the conventions of causal models, this node here, which is responsible for possible dependence between A and B, it's independent of the variable which is in this, which is corresponds to this node in the middle. And the node in the middle, I've called it hidden. I could maybe call it unobservable, and maybe some people would represent it with a square instead of a circle, or vice versa, I forget. But the point is A, X, Y, and B are observed. Hidden here in the middle is not observed. Experimenter is observed. I mean, we know what the experimenters do, but I'm assuming that what the experimenter did in advance to fix up A and B, to generate A and B may be independent and fair coin tosses, but they could be something else. But whatever they are independent of the stuff here. Okay, so there's a little causal model. And now we'll do some simple causal analysis, and we'll derive the CH-SH inequality, which is one of Bell's inequalities. So that graphical model, we can convert any graphical model represented by a DAG into a deterministic model where each node, to each node, there also corresponds an independent random disturbance, and the variable which is being represented by the node is just a deterministic function of any incoming variables, including its own local randomness. So there are behind A there can be some local randomness. Behind hidden, there can be more local randomness, but it doesn't matter. All the hidden randomnesses hidden or not, they are all independent of one another. And I'm interested in the model for the joint distribution of X and Y, conditional on the probability joint on the values of A and B. That's what we're going to observe many times: A, B, X, and Y, and do statistics with them. And quantum physics tells us something about the joint distribution of X and Y given A and B. And now we're going to see what classical physics would tell us about it. Not much, but something rather striking. So the graphical model says that the Alice's outcome, plus or minus 1, is some function of her setting, 1 or 2, just labels, and that stuff in the middle, which is the physics in all the apparatuses which in the experiment, and some possible physics in the detector, in the machine in her lab. Right? Now you may think of this as being stuff in the source, but you could also think of it as being stuff in the source and the transmission lines and the machines. It's everything which is sort of would be fixed in advance just before the settings are introduced. So actually we're going to merge this one and this one in a moment. Okay, so we have the graphical model says what I've written here. And it said, to be a little bit more precise, it says that the joint distribution of A, B, X, and Y can be represented in this way. So it does not say, so this is where some philosophy comes in, or metaphysics. I'm not saying that this is somehow the real physics. And we're not saying that lambda hidden is in the source or comes from the source, and that lambda X is sitting there as something real in the apparatus. We are allowing for randomness, which is for apparent randomness caused by chaotic behavior and et cetera, in a classical physical way, producing what is effectively randomness for our purposes. So there are no metaphysical or philosophical assumptions about even about randomness here. All that randomness could be pseudo randomness. I mean, it could be chaotic systems producing in a deterministic way stuff which looks random. That's somewhat important. Okay, I said that here. Okay, said a little bit more there, but move rapidly on.
Yeah,
now,
Richard, that's I have a question. May I have a question?
Good. Yes.
Oh, good.
What is the question?
Yeah, that's the you mentioned about that the slightly philosophical discrepancy between that true randomness and the pseudo randomness. That's
I say that it yes.
Yeah.
Carry on. I mean, I say that the distinction could be thought to be philosophical.
Yeah, but
let me say
in the reality, yeah, in reality, and that yes. We wanna to confirm the quantum mechanical evidence on the violation of the Bernoulli inequality in some sense. But
yes,
we need that the true randomness that's needed, that's the quantum mechanics prediction. Then that's the how to prove there is the how to learn on that's the meaning of this experimental demonstration.
You're absolutely right. So yeah, I mean the field of Bell inequalities is sometimes thought to be a field of metaphysics, and the Bell experiments are sometimes called experimental metaphysics. So actually we are doing experiments which are supposed to give us light into the absolutely foundational issues in physics, which usually are left to philosophers. And so like the distinction between true randomness and apparent randomness is also what this is all about. So it is all very tricky, okay? But still, so I think, I'll tell you later, if I keep on talking for an hour, I will get to the end of my slides.
Yeah. It's okay, right? Yeah, I'm waiting for that.
Right.
Good.
Yeah, great. I will tell you what I actually think, but it's only what I think, and other people think different things. Because I think, indeed, at this moment, I'm sure at this moment, that some of the issues here are always going to remain, in a sense, metaphysical. They're going to remain philosophical. They're not experimentally distinguishable. But on the other hand, the physical models can be more or less useful and more or less simple and more or less appealing. And physics succeeds by seeing that things are actually more simple than they appear. And that's what we're looking for all the time in physics. And when we find it's more simple than it first appeals, then we learn how to use it. And that leads to all kinds of good things and bad things. But yeah, right. Okay, now let's get to some, so now let's get some simple maths. And this is simple maths of the mathematics of classical probability, which doesn't explain randomness, it merely describes probabilities, the rules they should satisfy. And sorry, this this model is a classical, well, it is the kind of model which Einstein would have believed in. This is how Einstein would imagine what was really going on in such experiments, which had not been done in his lifetime. And he spent his whole life trying to combine quantum mechanics and relativity theory, and he failed. But this was the direction he was thinking. And other people too. And plenty of them are still around. They're still looking for a deterministic, classical explanation or hidden underlying mechanism behind what we see in quantum mechanics. So according to lots of famous people, some with Nobel Prizes and alive, like my colleague Gerard Hoofd in the Netherlands, the truth is actually classical, but it's even more weird than we imagine, but it is classical. And they try to get around the non-locality by ideas which I think are far-fetched, but which might be useful when you're doing cosmology and you want to make a model, a mathematical model of the early universe, right? The maths which such people are inventing might be the right maths, but I mean, nobody's doing experiments in the early universe except possibly God, choosing which path the universe is going to take right in the beginning. Then after that, it's all just clockwork, right? Okay, so now I'm going to define some counterfactual variables, and I've written them out here, but I'll say them in words. X1 and X2 are the outcomes which Alice would have seen had she chosen setting 1 or setting 2. And Y1 and Y2 are the outcomes which Bob would have seen if he would have chosen settings 1 and setting 2. And they are both just functions of the setting, which is just a label. I mean, it's a binary choice, 1 or 2, and all kinds of other junk from all over the experiment, which we are thinking of modeling as classical random variables, but which is not really saying anything. It could just be, I mean, coin tosses are completely deterministic things for practical, I mean, truly, I mean, there's the laws of Newton and some more about the air pressure and stuff, but a coin toss is a completely deterministic, can be understood to be a completely deterministic process whereby the outcome is merely a deterministic function of variables at the initial moment of starting to toss the coin, such as whether you put the coin this way up or this way up, how fast your thumb flips, that determines the angular momentum and the vertical momentum of the coin as it leaves, like where you put the table, how you catch the coin. The air on the way is going to have some effects, of course. Classical physicists believe they know everything about what happens there. Though, of course, actually, if you truly believe in quantum mechanics, at some stage, what that coin does is going to be influenced by quantum behavior of little particles it bumps into on the way. So maybe underlying the coin is actually quantum randomness. And of course, many believe quantum mechanics is it. It's everything. That's how the universe unrolls. And then they worry about the randomness, whether it's really random or not, whether it's relative frequencies or just what's the word? Well, it's like subjective. We happen to be in one branch of the universe, but all the other branches are equally real. Okay, now we define 4 binary random variables. They're the outcomes which we would have observed had Alice or Bob put in either of the settings which they could have used. And it's independent by the model, statistically independent of the actual setting choices. And this is the, I forget what this quality is called, but it's has a word in theory of causality. This is the formula which is connecting the counterfactual world to the real world. The actual outcome is identically equal to the outcome which Alice would have got if she would have chosen the setting which she actually did choose, right? And Y is YB. Conditional on the settings, we actually observe the outcome which we would have observed if we did choose that setting. And Bob does observe the outcome which he would have observed if he had chosen that setting. So this is, this is the counterfactual stuff. Therefore, the expectation of the product, conditional, as this is by definition, conditional on settings. So that's something we can get statistical information about, is equal to the expectation of the product of the counterfactual outcomes. Right, now, ta-da. Okay, so I just repeat. Now, please notice this little identity. I have to explain you, well, you may see it in a flash. Here are the products of all the counterfactual outcomes of Alice with all of those of Bob. And there are just 4 products. And I have one of them with a minus sign and the other 3 with a plus. And I factor them, I group them and factor in this way. And recall that since x1, first of all, since y1 and y2 take values plus or minus 1, these spin outcomes, either y1 plus y2 equals 0 and y1 minus y2 equals plus or minus 2, right? It could be minus 1 and plus 1, and then this would be minus 2. But if this is minus 1 and this is plus 1, then this one would be 0, right? x1 and x2 are also plus or minus 1. So this whole thing is equal to plus or minus 1 times something equal to plus or minus 2 plus something else which is 0. So this whole expression only takes the values minus 2 and plus 2. And of course, you can just check that by having R print out all 16 possible values of this expression as x1, y1, x2, and y2 take all possible values minus 1 and plus 1. Right? So this is, I mean, this is so trivial. John Clauser spent days well, actually looking at an earlier proof of Bell of a bit other different inequality, but nearly the same. And later Clauser improved the inequality to the one you see now in order to make it better useful for experiment. But anyway, take the expectation value of this. Expectations are linear. And okay, and use this fact, expectation of x1, y1 equals the expectation of xy given a is 1 and b is 1. And we get this. And okay, we're averaging something which could be -2 or +2. The result has to lie between -2 and +2. Right. This is the inequality of Clauser, Horn, Shimoni, and Holt. Here's Clauser again, and 3 guys who are now all dead, I think, and hence do not get the Nobel Prize. But Clauser is alive, and he gets it and deserves it. This was proven in 1969, written in a paper which nobody much took any notice of, and which Clauser used in their first experiment. Clauser and Friedman. And this was the first experiment. Okay, now I think you'll be glad things can sort of speed up a bit, because I don't have too many difficult things. Do you guys want to have a break or anything like that? It's 9:30. It can be finished by 10, so I can be finishing.
Yeah, I think go out. Yeah.
You want me to go on? Okay. Well, otherwise, just go and walk out, go to the toilet, get a glass of water. I will carry on. You can, if you miss something, you can ask me to repeat some things later. The slides are already on the internet, and they're already a bit better, so they'll be on the internet again. So this was Friedman and Clauser, and Friedman was a PhD student of Clauser, and if you read the book I told you about at the beginning about the history of this, you can find out how Friedman and Clauser managed to do this experiment, even though everybody thought it was an incredibly stupid thing to do, and it was a little bit expensive. I mean, they had to. Clauser wrote that he was like, what's the name for people who dive into dumpsters? I mean, he went around labs jumping into the waste bins looking for stuff he could use. And he needed one expensive thing, and he begged and begged and got it from somebody else. And by the way, he got a positive result. He showed that that inequality was violated. he got something in the direction of 2 square root of 2, which is bigger than 2. Remember, 2 square root of 2 is 2.8 something. Clauser showed that Bell's arguments were experimentally verified. 2 other people had done an experiment about the same time, and they got the wrong answer. I mean, they got an answer between -2 and +2. So this was not, I mean, this was not the end of the story. There was now one experiment which gave Bell's expected result, sort of, though Bell didn't know what to expect. He was not sure that quantum mechanics was right. He didn't really know what to expect. He was smart enough to realize that we can't know. And Clauser was smart enough to realize that we don't really know till we've really done a really good experiment. And this experiment was good, but somebody else did another experiment and got the wrong answer. Nobody talks about them anymore. Clauser did not do the first Bell experiment. Somebody else did. It gave the wrong answer. Nobody talks about it anymore. Now, there's an important thing in Clauser's experiment, which was a bit like aspects with 2 photons going through, well, actually not very far apart at all, but he has 2 photons going to 2 detectors. And the fact of life is that most photons arriving at a detector are not detected at all. Well, it depends on the detector, and it depends on the photons and the technology and the wavelengths and all kinds of things. And it's getting better all the time. But in his time, you did not know that there were 2 photons going like this. There may have been or may not. Either of those detectors might do something or might not. And most times they didn't. And he needed an assumption, which is a physics assumption, but a physics assumption which cannot be tested, as people have rapidly discovered. all photons which arrive at a detector have a probability of being detected that is independent of whether or not the photon has passed through a polarizer. Oh, well, okay, so there's two photons going like this. On the way they pass through a polarizer, some go through, some don't. Then they are measured by a photodetector, and he assumed that the probability that a photon went through, which is the same as close to the probability that it's ultimately detected at all, doesn't depend on how the detector has been, the whole apparatus, the polarizer has been set up. Doesn't depend on Alice's choice. But that's an assumption which you can't test, as was rapidly shown. I'm not sure if I have if that's in the next slide. Let's see. Yes, already in 1970, so that's even before this paper came out, a very brilliant guy who I think is still alive, and I may have put an E here which shouldn't be there, or vice versa. I get confused with the famous pearl of Judea pearl of causality. This guy's called Philip Pearl. He's very, very, very brilliant physicist. He showed that those quantum looking like correlations could easily have a classical physical explanation if you allowed that the detector, the chance of detection depended on the way the photons are being measured. And it's a simple model. It's a simple example of some tricky maths. His paper has got some misprints in it. I think I'm the first person who saw the misprints and corrected them and did classical simulations of it. So, okay, I mean, this is not terribly important, but if you want to know what Pearl did, then you could have a look at my paper, my recent paper. Okay, so already in 1970, it was known, and this was published in Physics Review D, so everybody read this, well, I mean, could read this. Already in 1970, everybody knew that Clauser's experiment would not prove anything, could not prove anything, all right? Very important. Well, the second loophole was that the settings should be chosen while the photons are in flight. Bell kept pointing this out because otherwise yet unknown physical mechanisms could ensure that Alice's apparatus sort of knows the configuration of Bob's apparatus, and it knows the setting which Bob is using. And therefore, the statistics can be anything from a classical point of view, absolutely anything. In fact, they could violate quantum mechanics. I mean, they could be bigger. There's a theorem which says you cannot get bigger than 2 squared root of 2, ever. And I know colleagues in Leiden who did an experiment where they got 3.1, which shows they did not understand what they were doing. There were some errors in their logic and in their experimental protocol. But okay, you find out that a lot of physicists who do experiments, they know about the experimental side, they don't really know about the philosophical side. They don't want to know about the philosophical side, so they just do an even better experiment than the other guys have done because of their experimental skills, which is very important, which is what their life is all about. And they do things which are impossible and not know, so that's fun. But anyway, so Aspect and 2 friends did an experiment where the switches were between this and this and this and this were so fast that this detection apparatus could not know what that detection apparatus was doing. Now, actually, the switches were operating deterministically. So actually, like the entire universe knows what both detectors are doing. So there's also another loophole here, which I will get to, but a philosophical loophole. if you believe that the only influence from here to here can happen through a signal going from here to here, well, still, yeah, then that, and that the signal only could contain the current setting, then you're with Aspect, and his experiment gives 5 standard deviations violation of Bell's inequality. Right, but actually almost all of Aspect's photons didn't even arrive at the photodetectors. So what Philip Pearl had shown 10 years earlier, and Aspect was very well aware of, means that this experiment does not really prove anything. Of course, no experiment really proves anything. Every experiment only proves something conditional on what you're prepared to believe in advance, or argue, or convince people. Okay. Now the third loophole. Okay, this is a little loophole of mine, which I'm not going to talk about. I mean, not of mine, it was being invented long ago. You're doing this experiment many times in the same laboratory with the same apparatus. And while you're doing that, all kinds of things are changing. The temperature changes, there are vibrations, things move out of alignment. The physics changes, like the parameters of the physics of this whole thing changes. And it means that you cannot, or should not, you should try not to assume that you have got IID trials. The idea that you have got independent, identically distributed copies of X, Y given AB for each of the 4 possibilities for AB is, frankly speaking, false. If you look at your data well enough, you'll see that it's false. You can see that it's false in numerous ways. You know it's false. So something could be done about that. Something can be done about this. And I learned it from my work in martingales and counting processes. And I was very pleased to be able to use a simple martingale argument to show how to deal with the memory loophole. And I did it in 2001 in a paper which I didn't think was particularly important, because it was just part of a quarrel with another guy who gave talks about how there is a classical physical explanation of these experiments. And I thought he was bullshitting us. And we started a bet together. And he was going to write computer programs, rather he had a slave who wrote computer programs for him. And he had a simulation. He went around to conferences, Luigi Accardi, with 2 computers and some wires between them. And he did simulations of Aspect's experiment in which he got the quantum mechanical predictions, and it was clearly completely deterministic. I mean, it was all randomness was local and pseudo-random, and he got the quantum results. And I made a bet with him that he wouldn't get them if he took some simple precautions. And the simple precaution was that he wouldn't be the guy who made the settings A and B. I would be the guy who made the settings A and B. And I would make them by tossing fair coins. And I would give them to him 1 pair at a time. And I would give Alice's setting to one of his computers and Bob's setting to his other computer. And then I proved using simple martingale argument that he would not violate Bell's inequality. And we had we were betting €1,000 and then later €5,000 because it needed to be higher because it was more difficult for him, but he knew he could do it. And we had a jury who was going to independently decide who had won the bet. And the jury did not rule, did not state that my rules were the good rules. And so we never actually did the bet. The negotiations about the bet failed because the jury was too, okay, I won't say what they were too, but they were too cautious and scared or whatever to prejudge on the basic rules of the bet. Okay, now my 2001 results were later improved, and they were picked up by the physicists, and they actually used them. So there are 4 big experiments in 2015, and all 4 of them cite either this paper or another paper at the same time. And I talked to the people in Delft, and they proved a better result than mine, right? So nowadays they use a better martingale inequality than mine, with a shorter and a much more cute proof. But anyway, I think I deserve a tiny bit of the Nobel Prize, but only a tiny bit. But anyway, it was great fun. Right. So now we get to the experiments, and we're still not close to Zeilinger. I haven't said much about Zeilinger yet, but I'm shortly going to say a lot about him. You will be glad to know. But one of the things I'm going to say about him is a slide with some algebra, which you might not, well, I mean, it's sort of baby algebra, but you might find it a bit disconcerting. In 2015 and 2016, 4 experiments were done by 4 different experimental groups. And 2 of them, Delft and Munich, used rather different technology than 2 others. NIST, that's Boulder, Colorado, but I think the group was led by a guy called Paul Kwiat in Illinois. So I could maybe also say Illinois or Chicago, Vienna, but the experiment was done in Boulder, Colorado, and Vienna, and Zeilinger is from Vienna. So he was like the senior author in this experiment. And all of these 4 experiments have long lists of authors, and the first one is the PhD student whose experiment it is. In other words, this is going to be one chapter of their PhD thesis. And the last author is the big guy who runs the lab and brings in the research money. And in between are lots of people. And some of them are theoreticians who do theoretical physics, and many of them are experimental physicists. And the claim is that these experiments took care of the memory loophole, the detection loophole, and the locality loophole. And what's left, it is claimed, are merely metaphysical loopholes, which means loopholes which you can't close by doing the experiment better. It could be that everything was determined at the time of the Big Bang, and everything just unrolled deterministically, right? It was all preordained. Some people have a religious point of view which makes them believe that. It's called Calvinism. You know, it was determined at some point by God whether you're going to go to heaven or to hell. Too bad. Superdeterminism. Another one is retrocausality. I mean, so that means that messages from the future influencing the past. No, yeah, it's possible. I mean, who's to say? Well, I mean, there are physical models for quantum mechanics which make use of formulas which are sort of shouting retrocausality at you. There's one way to solve Schrödinger's equation where you get away from the past and away from the future, which meet and interfere where we are now. So now is determined by interference between waves from the past and waves from the future. That's called retrocausality. Right. Now, all the experiments could be improved somewhat, a little bit, because they have some defects, and say a little bit about that. Now, what made this possible? Yeah, this is where Zeilinger is going to come in a big way, because Delft and Munich experiments are really the, I think, more important ones. And they use a very different idea. Instead of having 2 photons going like this, they have 2 locations, and at each location there's something fixed, macroscopic, physical object. It's excited by a laser in each place, and 2 photons go to an intermediate place. So it's the picture I gave you before, but reverse. There's photon going from Alice and a photon going from Bob. It meets at Charlie. Charlie measures the photons in the middle. And he does that every time anyway. And sometimes he gets an interesting result. Alice and Bob have no idea what Charlie is getting. They have got their physical thing. It has been excited by a laser. It shoots off photon, maybe. I mean, that's what they imagine is going on, but nobody knows, of course. And now their spin half system is in an excited state, and it doesn't stay excited for long. It shortly decays from the excited state to the ground state, or something like that. I mean, you can, it may or may not decay or whatever, and you can look at it and find out, is it excited or not? And you can look at it in different ways. So some local measurements are done of different kinds. So that part of the story is the usual story, but the intermediate part of the story is backwards. And the idea is that if 2 photons arrive here, if they are both measured after interfering with one another, so they go through a polarizing beam splitter from both sides, two waves go through some cunning little device, and they come out on the other sides of it, and it's like, here you get wave 1 plus wave 2, and here you get wave 1 minus wave 2. So here you are creating Bell states, or a Bell state. Then you measure those 2 photons, and if this one says yes and this one says yes, which only happens very infrequently, then you know later, I mean retrospectively, you know that on that occasion, those 2 spins, when they were measured, were in a Bell state. And that's something which is really due to Zeilinger. And I'll show you the maths. Okay, so this is, okay, I'm calling Charlie now, calling him Carol. So we're going to study the correlation between X and Y, conditional on a certain outcome of Carol and given the settings of Alice and Bob. So it's actually what we call a 3-party Bell experiment. And Zeilinger has been pioneering Bell experiments with not just 2 persons, Alice and Bob, gets a bit boring, but let's do Alice and Bob and Carol, or Alice and Bob and Carol and Dennis. You know, it goes on and on. Okay, side remark about the other experiments. Here's the idea, and here you see Zeilinger's name, and here you see a guy who's quite famous in China, who is a former PhD student of Zeilinger, and he's the first author here. So he is the guy who put this in his, I'm not sure if this is probably before his PhD, I'm not sure. This is about the year 2000. Experimental entanglement swapping, making photons entangled which were never ever saw one another. Because the idea is to get this photon entangled with this photon. And it needn't be photons, it can also be solid state devices. And you need to have 2 sources of entangled photon pairs. So this is Alice place and this is Bob place. And here's Carol in between, measures the 2 photons which arrive. And conditional on what Carol finds, this photon and this photon are now correlated. Nothing surprising about that from a statistical point of view, right? 2 independent random variables, 2 random variables here, 2 random variables here, 1 and 2 are dependent, 3 and 4 are dependent. Given some function of 2 and 3, 1 and 4 can be dependent. That's all it is. But it's not all it is, because they can be quantumly dependent, and that is kind of dependence which cannot be explained classically, as I've already shown you. So this is from that paper of Pan and 2 other famous guys and Zeilinger. And that might be a bit too much. Well, I mean, okay, that's abracadabra. Here's the, oh, okay, sorry. Here's the maths. Here's the maths. But, right. What have I got here? This is a very, very short notation. There should be a 1 over square root of 2 here. And these are two, well, this 0, 0 and 1, 1 are represent states of 2, say, photons of Alice. So this is 1 over square root of 2, apple, apple plus orange, orange, if you like. And this is the same thing, but these are Bob's place. Well, these start at Bob's place. So there's a 1 over square root of 2 here, a 1 over square root of 2 here, and I should put a straight bar here and an angled bar here, and a straight one here and an angled bar here. And maybe I should put some subscripts on everything to indicate that this 0 and this 1 corresponds to Alice's first qubit. This 0 and this 1 and this, no, yeah, this 0 and this 1 correspond to Bob's second qubit. No, Alice and Bob, no, sorry. Alice's first qubit, Alice's second qubit. Alice's first qubit, Alice's second qubit. Bob's first, Bob's second. Bob's first, Bob's second. Anyway, they're just vectors in Hilbert space. They're 2 by 2 complex vectors. And there are 4 of them. And you can use the usual rules of algebra just to multiply things out and so on. And so this is a vector in C2 tensor C2 tensor C2 tensor C2, which is whatever it is, 2 plus 2 plus 2 plus 2. This is an 8-dimensional, yes, I think it's 8-dimensional complex vector. But actually in the basis, it's all consists only of zeros and ones. So here are, here's Alice's first, Alice's second, Bob's first, Bob's second. Now, and we have 4 of such terms. On this line here, I take the first one, 0, 0, 0, 0, and I'm going to write the middle 2 zeros because those are the ones which we send to Carol. Those 2 go to Carol. And I'm going to write 0, 0 as 0, 0 plus 1, 1 plus 0, 0 minus 1, 1. Okay? These are just vectors in Hilbert space. These are 4-dimensional complex vectors. 0, 0 is a 4-dimensional complex vector. Okay, I can do that. And then I leave the first 0 and the second 0 on the outside. This one is still stuck at Alice's place. This is still stuck at Bob's place, but we imagine this bit as going to Carol's place. I mean, this is what we imagine going to Carol's place. Why not? We can do that. And this as well. I do that 4 times. And then I get 8 expressions, you could say, in 2 groups of 2. And I notice that 0, 0 plus 1, 1 for, sorry, for Carol occurs twice. It occurs here and here. Here it occurs with a 0 and a 0 on the outside. And here it occurs with a 1 and a 1 on the outside. So I put them here. Now we've got 0, 0 plus 1, 1, 0, 0 plus 1, 1 for Carol. 0, 0 minus 1, 1, 0, 0 minus 1, 1 for Carol. 0, 1 plus 1, 0 for Carol. 0, 1 plus 1, 0 for Carol. 0, 1 minus 1, 0 for Carol. 0, 1 minus 1, 0 for Carol. So what has happened now is that Carol's qubits are entangled with Alice's qubit and Bob's qubit. And 0, 1, let me see, there may be a misprint here, but there may not. anyway, if you look here, there's 0, 0 plus 1, 1, 0, 0 plus 1, 1, and there's 0 and 0 and 1 and 1. So Alice and Bob together have got 0, 0 plus 1, 1. That's one of the Bell states. If Carol finds 0, 0 plus 1, 1 at her place. Right. On measuring the inside 2 qubits in the Bell basis, conditional on finding 0, 0 plus 1, 1, the outside 2 are also 0, 0 plus 1, 1. Now that should be repeated 3 more times. If Carol finds 0, 0 minus 1, 1, then Alice and Bob together have got 0, 0 minus 1, 1. 0, 1 plus 1, 0, 0, 1 minus 1. This is a misprint. This should be a 0. 0, 1 minus 1, 0, 0, 1 minus 1, 0. So I'm sorry, there's terrible, terrible misprint there. This one should be a 0. Right. And that's what they do. That's what they do. So many, many times, and this is sort of a picture of how they would do it, how they did it in 2 of those experiments. In Delft, not far from where I live, terribly far, by Chinese standards, very close to where I live, in Delft, like a kilometer apart, on the campus of Delft University, Technological University, they had 2 diamonds. And in those diamonds are little defects. And they had located a little defect in each of those diamonds. And the defect is that one carbon atom is missing. Sorry, 2 carbon atoms are missing, and they are replaced by a nitrogen atom and a gap in both places. You can engineer that, or you can make it lots of times, and yeah, you can create, you can industrially prepare those things if you want to. And each of those 2 nitrogen vacancy defects, to it is associated a spin. I think it's an electron, and it can be an excited state or a not excited state or something like that. And you can measure its state. And that state is a qubit. I mean, it's a qubit. It can be in a superposition of excited and not excited. And by the trick I've shown you, you can arrange that Alice and Bob's nitrogen vacancy electron spins are in one of the Bell states, almost exactly. When they are in that state, on those occasions, when Carol, who's sitting between with a beam splitter, this is not bullshit, it's a beam splitter, a polarizing beam splitter, I think, where photons from Alice and Bob interfere and go through polarizing beam splitters. Sorry, this is a polarizing beam splitter, and then get detected by photodetectors. And sometimes this one says click, and this one says click. And on the occasions that that happens, you know, retrospectively, according to quantum mechanics, that these 2 spins are in the Bell state. It's 10 o'clock, and I have skipped some slides. I hope it doesn't matter. I'm going to continue because, oh no, I can't continue. I want to show you how the experiments has been done better and better. And here's another young Chinese guy, but he came from Shanghai, went to Amsterdam for his PhD, and he's now a postdoc in Munich. And he's got his first paper with a heap of other people in Nature. So this guy will probably have an interesting physics career. He's an experimentalist, and he does device-independent quantum key distribution between distant users. And they did this experiment, and okay, this is like once you get used to it, one starts to recognize things here. Here is a quantum random number generator. This is creating settings, I suppose. And it's sent to some device, but it's also stored on hard disk or whatever. And similarly, Alice's state. This says fiber beam splitter, not bullshit. And here are single photon detectors. And basically, what this experiment is doing is it's doing two experiments at the same time, or interleaved. It's doing a Bell experiment, and it's doing a Bell experiment with very, very good statistics. And you could call it loophole-free, though some people might complain that this distance is only 400 meters as the crow flies. If you believe that the photons went through the glass fiber, then they're 700 meters apart. But, you know, some people will say, yes, but 400 meters is not enough. Okay, right, so they need a bigger campus so they could stretch out their fiber longer. They are doing a Bell experiment, and it's randomly interchanged with an EPR experiment, where they measure the two spins the same way. They measure the two spins the same way, and they tend to get equal and opposite or equal results, always equal, both up or both down, because they use a dip. So they each are choosing between 3 settings, not 2, in order to do 2 experiments at the same time, a Bell experiment and an EPR experiment. And the EPR experiment is going to give them the quantum cryptographic key, which is shared between Alice and Bob, and nobody else, according to quantum mechanics, can know what it is, because they did a Bell experiment which almost hit the maximum of quantum mechanics, 2 square root of 2. And they have techniques to take care of the probability and a small amount of there can be a small amount of eavesdropping. They have with a big chance that they have got reliable bits. I should say also this, no, sorry. Yeah, in Munich, so Delft does these little diamonds, which is really cool. Munich uses a rubidium atom in an atom trap. Okay, so that's an atom of some pretty rare stuff, and it's trapped, and it has a spin which can be up or down, or left or right, or this way or that way. So they actually have different physical technologies, but the mass is identical. And this was Munich. The experiment I was showing you was Munich. And here's the data. And right, here's some numbers. And I could tell you an awful lot about these, explain them. This experiment is better than the previous ones because the numbers are much bigger. At least the Munich numbers now are much bigger than the Delft and the Munich numbers before. So that's a really great thing. They're so great, I'll show you some p-values, that if you compute 3 correlations minus the 4th, and you compute a standard error in a classical way, assuming multinomial distributions, assuming IID data, of course, which is possibly not true, you get a value of 2.6, which is not too far off from 2.8, which is 2 times the square root of 2. It's a bit far off, but it's way above 2. Standard error is 0.07. The Z value is 7.5. If you use conventional statistics, assuming IID, the p-value is 9 times 10 to the minus 15. Now, I know how to get a better p-value, and I can't really tell you about it now. Because my wife is going to come in and bother me quite soon, I'm afraid. And I get a slightly smaller S and a slightly smaller standard error and a bit smaller Z, right? This is 0.577 divided by 0.07. So my p-value is only 1.4 times 10 to the minus 12. And I think it is much better. I think it is much more accurate. Though, on the other hand, who believes a p-value like that? I mean, I'm using the central limit theorem and the law of large numbers, and I'm assuming IID data. And I don't really believe in IID data. And I know the central limit theorem, even if n is 2000, still has pretty big errors when you look at tail probabilities. So the usual error in the central limit theorem for this p-value, tail probability, must be much, much bigger. But there's an alternative approach, which is to use my martingale method. And astonishingly, you get, I'm astonished, I get the p-value of 5 times 10 to the minus 13. And this is a much, much, much better p-value because this is immune to shifts during time in the statistics, in the physical parameters. And it's immune to jumps in them. It's immune to statistical dependence as time goes by. So it's immune to the memory loophole. It is based on an assumption, which is that the random number generators are close to perfect. Okay, and if you look at their random number generators, they are pretty perfect. But maybe in retrospect, this number is not this. I mean, this correspondence is an illusion, I think. But this Z of 7 is probably good, and I would say use Chebyshev's inequality. 1 over 7 squared is 1 over 49 is 1 over 50. The true p-value is maybe 2%. Okay, so I think that's a very reliable statement. They really got something pretty statistically significant for a very, very difficult experiment. And I wouldn't really believe these numbers. Yeah, what else could I show you here? So here were the raw numbers. So there were 400, this is the 1-1 setting. Alice does setting 1, Bob does setting 1. This is the 1-2. This is the 2-1. This is the 2-2. You see big numbers on the diagonal of 1-1, 1-2, and 2-1. And you see big numbers off the diagonal for the 2-2 settings. And here's some rapid numbers to get my martingale test as improved by the Delft people. And it's you add up the diagonal numbers of these three, you you add the off diagonal numbers of the fourth one. That's here. You get 1357. You add up all these four numbers, you get 1649. And you compare this to a binomial distribution with 1649 trials, 1356 outcomes, heads, probability of heads 3/4. And you look at the right tail probability. And 1357 divided by 1649 is 0.822. That is far away from 3/4. And it's this amount statistically significant away from 3/4. And 3/4 is basically the CHSH inequality. It corresponds to the bound 2, but it's sort of transformed or shifted a bit. It's converted from an inequality of correlations to an inequality of probabilities, I guess. Yeah. The sum of three probabilities minus the sum of the three probabilities of these outcomes plus the probabilities of these outcomes can't possibly be better than 3/4 if classical physics is true per shot. well, sorry, the shots go like this. Per successful shot, this probability for Alice and Bob can't be better than 3/4. Okay. Well, I'm very close to the end. I've told you this. Yeah, here's some references. Okay, here's some, yeah, oh, this is some self-advertisement. What does this all mean? Right, here's some pictures, but this is more for a discussion, if at all. There is something in quantum physics called the measurement problem, and it's all about what is real and what is not real. And this is a lovely, lovely picture which appeals to me from a very famous paper from 1991, that there's, according to quantum mechanics and conventional quantum mechanics, there seems to be some divide between parts of physics we use quantum mechanics and parts of physics we have to do classical mechanics. And actually we live in a classical mechanical world. Our observations are classical. They're written down on, I mean, they can be carved on pieces of stone. You see a 1 and it's going to be a 1 forever, at least till the end of civilization, right? And on the quantum side, things are sort of, cats can be alive and dead at the same time. And okay, you time goes by and you have a look and you find out that the cat now is alive and dead. But what it was before, quantum mechanics says it's neither. That's Schrödinger cat. Paradox. It's a paradox because it's an apparent contradiction. I had a debate recently with a guy called Gill who thinks that he thinks that quantum mechanics is local and realistic. But we debated this. It was great fun. He thinks he believes in local realism, but on the other hand, he doesn't believe in local hidden variables, which is subtly different because he has definitions of local and real, which are drawn from a philosophy and which are very reasonable, and they are very well reasoned. They're very good reasons to believe his definitions of local and real. What is local and what is real? And actually he has two kinds of, yeah, he actually does have a hidden world and an empirical world, and he distinguishes them all the time. Okay, now, okay, there's some stuff there which I won't say now, but we can look at it some more if you want to. I said to him, you have defined local and real. I understand your reasoning, but I don't like your definitions. An interesting thing which Brassard says is that he proves, actually it's a student of his who proves this, he's a very nice guy, a very, very, very smart young man, and I'm going to be talking to him some more. He says we, but he really means his student, who's now an independent researcher, shows that every no signaling theory with invertible dynamics has a local realistic model. This applies in particular to unitary quantum theory. Now, what they mean by unitary quantum theory is quantum theory without collapse, without wave functions collapsing. And that's one thing. And I have a completely different point of view about what Bell experiments prove. I think that good Bell experiments prove that the principle of invertible dynamics is wrong. Physics is not time reversible. I mean, some of the formulas, many of the formulas of quantum physics are reversible. Schrödinger's equation is time reversible, but measurement is not reversible. I think it's evidently not reversible. And other people say, yes, but in many worlds theory it is reversible. And I say many worlds is many words, it's bullshit. Okay, so you can argue with people over beers and or whiskey about that. I think that the Bell experiments show that the collapse of the wave equation is real, fundamental, intrinsic, stochastic, and one of the foundations of the universe. Right, so now I'm pontificating, and I'm an old guy, so you'll sort of believe me, but don't. But I say I think the universe is driven by quantum randomness, and the reason they still haven't really merged quantum mechanics and relativity theory, they are merely in a sort of friendly coexistence, like formerly communism and capitalism used to be in some peaceful coexistence for many years, and maybe they still are in some places, but they coexist in a sort of peaceful way because there is some compatibility between the two systems. But when you try to really unify them, you run into problems. And I think the problem is that the principle of invertible dynamics and determinism are wrong. And as long as the physicists of relativity theory hang on to those dogmas, it's written in their party book, this is what you have to believe, and this is what we believe. Everybody knows now that Einstein said this, and this is it. Einstein was more subtle, but people take things of Einstein and convert them into dogmas, which you must just believe, in the same way that people take things that Niels Bohr said about quantum mechanics, where he was either being very subtle or maybe a bit mixed up. There's debate about that, but he was very authoritative because he was always right, and he became a very old and famous man. And so everybody believed him, and then Feynman came along and said, shut up, just calculate, you can't understand it. That has been the dogma. Okay, I end with two pretty pictures. This is a sketch of an artwork by my daughter, and who I talked to about quantum mechanics, and she's a biologist and an artist. So this is my picture of the actual world, where I think of our consciousness as being these little specks of light, fluorescence, which you see in the waves as the waves crash on the shore. And briefly they light up. This is our brief existence, and briefly we are aware. And we have told us the story that the past is real, and some people think the future is real, but actually the past, I think, it's real. I take it as real, but it's frozen. We're not there anymore. We deduce it, and we have shared experience, so we discuss with one another, and we all agree that Venice was there last time we went to Venice, right? And we agree that it's probably still there now today, and I'm sure it is too. So we agree about the past, but we only experience them now. I'm into Buddhist philosophy and Buddhist meditation, by the way. So I should mention I visited some wonderful Buddhist temples while I was in China. Wow. Right. The future, according to my picture, is shimmering waves of uncertainty. I mean, they determine the probabilities of what is going on now. And once it's done, and it's gone, and it's irrevocable, it's fixed. What we are aware of is sensory impressions now. And from them, we deduce a picture of the world, which works very well, but it doesn't help us very well understand quantum mechanics. I think now here's the last slide. Another picture by my daughter. This is a small one. And the idea is that we are sitting on a chair in the waves and dreaming about the future and yeah, worried about the past, you know. So I'm going to stop now, but you can ask me anything you like. Okay.
Thank you, Richard. Thank you very much for a very nice talk. Richard, sketch the history. Okay. Yeah, we just sketch the history of Bell inequality and the interesting example of apple and orange. This is very useful for people living in macro universe to understand the quantum universe. Richard introduced the causal model for Bell experiment and discussed analysis of the experiments using the RDG Martin-Gill approach, Richard Gill Martin-Gill approach.
Yes.
Yeah, which I think deserves a Nobel Prize.
Yeah, me too.
Yeah, yeah.
I won't guess
and
it.
after all, Richard. Okay, yeah. Richard
by the way, sorry, I wanted to say I have written 2 papers with Zeilinger. I have visited him in his lab.
Yeah, I know that.
Yes, so I was part of the story. I'm very happy that the 3 guys got the prize who got the prize. You know, yeah, but it's a very wise choice. Yeah.
Okay, why the contribution of these statisticians are always ignored in the Nobel Prize?
Why? Yeah, well, physicists don't like statistics. Ernest Lord Rutherford, who was the first guy who saw the nucleus of atoms. He said, if you need statistics, you did the wrong experiment. This is the kind of philosophy of classical physicists. Now, this philosophy is changing because the quantum experimenters doing experiments now, they are working with probability, and they are working and statistics, and they're working with it in a very sophisticated way.
Yeah.
So the whole physics community as a whole may not be quite ready for it. I mean, it's taken 100 years, and slowly generations grow up and are replaced by and leave, and it's changing. So I think there's a big future for statistics. And in particular, you know, the experiments with quantum computers, that quantum computer may never ever come, but the statistics in showing that they got so-called quantum supremacy are classical statistics, very sophisticated, really tricky. And so I tell all the young people, get involved in this now. You're not too late. There's a lot more going on. And who knows? And you know things which I don't know. Every generation, and young people know things which the older generation doesn't know. And I was just lucky a few times. I had some amazing luck twice, you could say, in quantum, well, 3 times. I got a nurse out of jail. I did some martingale stuff in survival analysis. I did some cool stuff with my quantum friends. But I was just lucky 3 times.
Okay, you are so modest.
Well, yes and no.
Okay, after Richard showcase in this talk, he showcased the power and the potential of statistics and the causality in quantum physics. Do you have a few minutes to take care of questions?
Sorry?
Do you have a few minutes to take questions?
I do, as long as my wife doesn't burst in, and that may take a few minutes.
Okay, sure. So, so for the audience, if you have any questions, please open your microphone, and you can ask Richard straightforward.
Okay.
So let me ask a question.
Yeah, look, everybody's silent.
Yeah, I really want to ask this question. Yeah, I feel shocked about the violation of the reality and the locality from the experiment. Yes. So because particularly quantum physics, they will insist locality, right? But abandon reality. That for me, it means.
Yeah, but what reality? That's an opinion.
That's an opinion, right?
I have even written that in one of my papers. I have changed my mind about this several times. Right now, my opinion is something called convivial solipsism, which means solipsism, which means you sort of can't know anything because all you have is your senses. But convivial solipsism means you also talk to other people and you find out that they say things which makes you think that they are like you, right? And but I come to the conclusion partly from Buddhism and partly from physics, that now is real. There's a reality now, and it's changing all the time in a random way. That's real. The past is also real. There's a real past. It's frozen. Okay, we don't have access to all of it, but we can believe it's there. And so I also believe that the moon is there when nobody looks too, and I believe you are there, even though I only see some funny dots on a screen. And so maybe it's all maybe it's all a computer simulation. So I do believe that now is real and now is really real. I believe the past is real, but it's past, it's frozen. And I believe the future is unknown and that it is probabilistic, and the probabilities are determined by quantum mechanics, which gives you the probability distribution of the future given the past. And we sit here on the waves, and as time goes by, like more of the past gets fixed and the tide goes out or tide comes in, whatever, we are moving. We're always sitting there where the waves break. That's where our consciousness is. And I'm not saying that it's all in our minds, but I'm saying that's where our access to information is. That's something we can be sure is real, even though it's only temporary because we're only mortal. But we can share our experiences with the experiences of the other little dots which you see there. Yeah. So I think that quantum mechanics tells us that we should rewrite our conceptions of real and real and local. So quantum mechanics does not violate causality. It does not violate classical causality. That there is no way that Alice can send messages to Bob faster than the speed of light. You can use quantum mechanics to send messages from Alice to Bob. They will arrive encoded, and Alice is going to have to send you the key by the old-fashioned telephone. So you won't be able to read the messages from Alice, which she sent you by the secret quantum channel, which, like, you did some things in your lab. You did some measurements on a quantum state, and it was in an entangled state with something which Alice has. So she can, if you would believe in classical physics, then what is going on in there would be violating locality. But why believe in classical mechanics? Quantum mechanics tells us it's wrong. Successful Bell experiments show it's wrong. Quantum mechanics is insanely compatible with relativity theory. It's just difficult to merge in one theoretical framework, but it doesn't violate anything that relativity tells us. It only violates things that relativity tells us when you try to put a classical story behind what is going on. So, I mean, what I could say at this point, shut up and calculate, because why do you want there to be a classical story explaining everything when quantum experience is shouting at us that the world is random and run by quantum mechanics and does not violate causality? And some of the most interesting parts of it, there have been objections that some of the theories could not be made relativistically invariant, but they can. This has been done by now. So that's not you don't have to assume a unique reference frame. You don't have to assume that. So of course, when you tell baby stories about quantum mechanics, you assume things which everybody ordinarily agrees about space and time and so on. But you can make it as relativistic as you like, and still you get the same predictions. And people have done the Bell experiments on devices which are rotating so fast that you should take account of relativistic things, and that sometimes Alice's measurements are done before Bob's, and sometimes they're done after Bob's, depending on which part of the, right? I mean, you put the two parts of the Bell experiment onto spinning around things very, very fast, and you have measurements at different parts of this. And so it can't be that if you believe it classically, then somehow you have to believe that sometimes messages are going from Alice to Bob, and sometimes messages are going from Bob to Alice. I mean, they have done the most amazing experiments. And they keep showing that quantum mechanics is right.
Okay.
And I think it means we have to take it seriously. And we have to take it seriously by reconsidering our concepts of locality and realism. There's a question from my Japanese friend.
Yeah, hi.
Okay.
Hi, Richard.
Hi, Yutaka.
Hi, Richard. Thank you so much for your interesting talk. I have a question about that. You lastly sort of question you answer is undoubted. Is that you say is that classical mechanics is or sort of deterministic world cannot be explained on that side. After all, on the opposite thing, how to understand this? All the sort of our nature can be explained by the probabilistic scenario or just a statistical scenario. Can we explain that to everything?
Can we explain everything? Well, some people claim we can explain everything. I can't explain everything. I'm not a philosopher. I'm not a philosopher. I'm not a psychologist, and I'm not a physicist. So I don't have a sort of professional answer to your questions. You know, I don't know. And moreover, I have changed my mind like every 10 years since I got involved in this stuff. So if I live long enough, I'm sure it will change again. So I can't tell you what you should believe. You have to get the information, and if depending on your background in science, you may choose some stories better than others. I actually think that we cannot solve this. I think it has to be a matter of sort of philosophy or religion. In other words, it's a question of personality. If you excuse me, I mean, it's some people will find some kinds of explanations the right ones, okay, and other people will find other ones the right ones, and they will both absolutely agree on all experimental predictions. So you also don't have to choose. You don't have to choose whether you believe in God or not, because it doesn't make any difference. I mean, the world is the world. Some people get on better or feel better in their skin thinking that God is running everything, and other people feel better in their skin thinking that the chance is running everything. Most people find chance horrific, but I, as a probabilist and a statistician, find chance wonderful, and I know that chance is a wonderful creative resource. I believe that randomness is what drives the universe. I mean, I believed that before I got involved in quantum mechanics, but I believe that in a sort of philosophical way. I mean, my life is proof of it, because all the good things that happened to me were pure chance. Of course, all the bad things that happened to me were pure chance too, but that's how it is.
Yeah, that's good. Yeah, that's the I totally agree with you that about that randomness, and that's the most fundamental issue, and that's our understanding. That's it's nobody validated experimentally, and that's the true randomness is. This is also true.
Oh, I think it's an undecidable thing. I mean, yeah,
that's good.
Yes.
Thank you so much. Yeah.
Okay.
Thank you. Yeah.
Thanks for your question. Any more questions? I'm getting pretty exhausted, by the way.
Okay. All right. Thank you.
Coffee or whiskey.
Any other questions? So actually, I have a few another questions, but I think I will ask later by email.
Oh, that's fine. Yes, anybody can. Please, everybody, feel free to contact me in any of many ways. And I'm on Facebook. I sometimes look at Twitter, but I don't follow it. I have several email addresses. You can easily find them. I love discussing with people, and I love fighting with people, because my best work was done because I disagreed with somebody very strongly, and I wanted to prove they were wrong. So they got very angry with me, but it did lead to some of the things I'm most proud of.
All right.
Okay. So watch out. I may love to fight with you.
Sure. Thank you. And let's thank Richard Gill again for today's talk, and I look forward to meeting you in person in future. And you're welcome to visit us in the future. Yeah. And thank you, and thank all the audience, and thank for the questions. Thank you, Richard. Now this is the end of our talk. Bye.
Bye, everybody.
Bye.
I had fun. Thank you very much.
You too.
Yeah.
Have a nice day.
Thank you. Okay, right. I'm going to start quitting now. Where's the button? Oh, escape. I'm going to stop sharing now. Stop sharing. Okay, what's that? Oh, Christ. So now I'm going to leave. Leave meeting.